talk on the Schrödinger operators on non-simply connected manifolds. Please, Iskander Hasanovich, you can.
The sound is okay? Do you hear me quite fine?
Yeah.
Yes, we do hear you, but we don't see your presentation yet.
Yes, how to share it?
There is a button, поделиться.
Where is the button? Share.
Just near the exit button.
Yeah. Okay, I had to.
But you need first to open your PDF file.
It's opened.
Okay, so you choose. Yeah, we see. But it's.
You see it?
Yes, we see it. Okay. So please.
I don't see that you see. Okay, but still, I'm starting. Yes. First, I would like to thank organizers for the invitation to give a talk. And this is just some observation about the possibility to extend the notion of Floquet block functions from Tori to a more general setup. Actually, this talk came from some other considerations about which I shall speak at the end of the talk, on the very last page of remark. And the title is called On the Schrödinger Operators of Non-Simply Connected Manifolds. What are the Floquet block functions? I mentioned the definition in the general setup. Assume, we have its classical setup. Now, when we consider, in one-dimensional case that was Floquet, and many-dimensional case that was Bloch, so we can say Bloch functions for shortness. Block functions on Tori. We have an n-dimensional Schrödinger operator on a torus. So this is an operator just with periodic potential U. It is periodic with respect to some lattice lambda of maximal rank. So if we factorize n-dimensional Euclidean space over this lattice, consider the quotient of that, you will get a torus. So that's with different conformal classes. The conformal class of a torus depends on lambda. In physics, usually the torus is the generators of lambda are orthogonal to each other. But nevertheless, we can consider that in a very general setup. Let's psi is a formal solution of the equation L psi equal E psi. We shall call E energy. And psi is almost periodic. So this is, if we shift the argument of psi by eta, the eta is the vector from this lattice lambda. The psi is multiplied by some function exponent of some quotient, which is of some multiplier which is linear in eta, in this vector lambda. It's called the Floquet block functions with quasi-momenta k. K is just the vector from n-dimensional complex valued vector. The simplest example, the classical Floquet functions, then the n is 1, and so we have a lambda is tz, so we have a line, a periodic operator on a line. T is a period, and then psi x plus t is equal exponent I k t psi x. So this is the classical definition of the Floquet function from the 19th century, and for in general, its definition of the block function, which was introduced by Bloch in the study for quantum mechanics in the physics of crystals. So, what is the Floquet block spectrum? What we can say about the possible values of E and K, quasi-momenta. They are related by entire function. So given L, there is an entire function f, which depends on n plus 1 variable, such that f equals 0, if and only if there exists a Floquet block eigenfunctions, such that Z0 is the energy of this corresponding eigenfunction, and the Z1, Zn, these are quasi-momenta of this eigenfunction. So, so actually, we may consider the f as the equality f equals 0 as the dispersion relation for these physical quantities. So actually, it's actually how it has to be treated. The set f equal 0 we call the Floquet-Bloch spectrum of n. Again, the simplest example. N equal 1. We have two variables, E and K. We have dispersion relations, how energy depends on K and how K depends on energy. And we have to notice that, you see, there is how K comes into the definition. So, so K in this one-dimensional space, K is defined up to 2 pi divided by T, because if, for instance, if a one-dimensional case eta is equal T is a period, and we add to the to K eta the quantity 2 pi over T multiplied by T, you will get the same values of exponent of this linear form. So actually, quasi-momenta are defined with respect to shifts by inverse lattice, 2 pi and inverse and dual lattice. Dual lattice actually to lambda. So now we take this spectral set, spectral variety f equals 0, and take the quotient with respect to this action of the dual lattice. In n equal 1 is this just shift by 2 pi over T. And this would be the spectral curve for the one-dimensional periodic Schrödinger operator. I had known about the spectral curve from the outstanding article by my teacher Novikov on the periodic problem for Carteverde-Friis equation. And in this setup, spectral curve plays very important role because first, originally from the article by Novik, the whole spectral curve is the first integral of the KdV flow for periodic potential in the class of periodic functions. And then it appears after works by it, Matveev, that Brovin, that the inverse problem for finite gap potentials is solved in terms of some spectral data. This is this spectral curve, some additional algebraic data on this spectral curve. And if this spectral curve is curve means it's this one-dimensional complex manifold. In fact, of course, it's a Riemann surface of real dimension 2. And the function, in the case if this surface is of finite genus, then the potential is reconstructed from this spectral data and is expressed in terms of theta functions of this Riemann surface. But there is this general proof. It's not complicated. I did it for two operators in middle 80s. Didn't publish it, but it was referred in this survey by Krichever, a Russian mathematical service about two-dimensional periodic Schrödinger operator. And I will mention one. I only published it later in the 90s, then introduced spectral curves for Torre in R3, and in this case, the spectral curves were corresponding to two-dimensional Dirac operator with periodic potential. But there is one derivation of the existence of a spectral curve for another operator, which I also did find in middle 80s and explained it this time to Krichever. And actually, he wanted to refer to my article, and the article there is reference Taimanov. He just figured out some title of the article, but the article is never published, but the reference exists in a Russian mathematical service in 89. So we can do the same for the operator hyperelliptic or heat operator. Let's take L equal exponent epsilon dy minus dx squared plus the potential. For simplicity, let us periodic with respect to x and y with these periods. It's for, of course, that's 4 periods. There are two important cases of this operator, special cases, which are common in soliton theory. Then epsilon is equal 1 and an epsilon is equal I, the imaginary unit. Let's first consider epsilon equal y. Then the operator is hyperelliptic, and we can take such a value, real value complex E naught, such that there is existed inverse operator, dy minus dx squared minus E naught. It maps from L2 on a torus into W21 on the torus. This is, I don't know this. Don't know how it's called now. I think it's sometimes it's called Slobodetsky spaces, but it's actually Sobolev spaces of the function of the torus, which has two generalized derivatives in x, one generalized derivative in L, and with respect to these derivatives, these derivatives are squared integrable as well as this function. So the psi, the block function of this operator, this is a psi. How it looks like. For this special value of periods, it would be just this exponent, ikx by Ly phi. I took this for simplicity, you will see, for simplicity of computations. So we have L psi equal psi if and only if. That's easy to check. And I forgot here has to be the quantity 2ik dx also has to be added here. This quantity, it was skipped here. If it's this operator of phi equal E phi. Therefore, taking the inverse, applying to this operator, so we have that phi has to correspond to this equation. What is this operator? The right-hand side. We have the inverse operator which maps to the W212. Then this multiplication by bounded potentials E naught minus E plus U plus EL minus L. This is can be considered as the composition of the embedding of this L minus 1 phi into L2, and then multiplication by these functions, by this quantity. So the embedding is compact. Multiplying by this quantity, you do have again continuous operator. The composition of continuous and compact operator is compact. This derivative, it maps W212, it maps into W1 1 over to 2. That's another Slobodetsky space, this fractional exponents. And then again, there is an embedding into L2. And embedding would be compact operator. So we have the definition. So we have the last equation has the following form. It's the unitary operator, unit, plus multiplication, plus some polynomial pencil of compact operators from L2 to L2. And the paper, I don't know, this analytic Fredgon theorem, later I found it in Reed Simon in volume 3. It's referred in many places. But I had known actually from Andrei Shkalyak about the Keldysh theorem in his famous article from 1951. So that for such polynomial pencils of operators, there exists an entire function. This is the regularized determinant such that f equals 0 if and only if this equation is solvable. So because it's the derivative, the proof of this theorem was given by Keldysh again in his survey in 1971 in Russian Mathematical Service. There he gave the expanded, let's say, unzipped version of his very short article in the Cloud of Soviet Academy. So now what we have, this operator then epsilon equal 1 enters the last representation of KP2 equation, for which the spectral curve exists by this Keldysh theorem. This spectral curve gives you the first integral of the flow. And also, what is important here is that it's known from other points of view. This notion is quite vague in physics that some system is integral. But it was known that from other soliton approach, from other approaches to construction of explicit solutions, that KP2 is considered and was considered as an integrable system. So this explains partly from this point of view, so spectral curves, the integrability of this equation. Let's take KP1. It was assumed as a non-integrable equation. This operator is non-hyperelliptic. Look, because here we have to replace EL by L minus K squared. This operator is not always inverted. If we take U equals 0, so this you will get some small denominator. So this is not inverted. So the spectral curve doesn't exist, and this KP1 equation is not easy. So here we use this Sobolev spaces with homogeneous exponents and even fractional exponents. But for proving this theorem, when we're speaking about this Schrödinger operator, that's much simpler. This is inversion gives you W22, and then you will get the easily compact operator. So this is for these systems, then epsilon is equal 1, and that is Schrödinger operator. You can prove the existence of the spectral curve. This is, you can say, Bloch variety and so on. Now I would like to consider its generalization on the more general situation. That's just very recent considerations, very recent. Let them be a compact manifold without boundaries, so it's closed manifold. I said that compact without barring just because here the talk is oriented for specialists in function analysis and spectral analysis, and for them it's necessary, it's helpful to explain what means closed manifold. Now compact without boundary, it's well understood by anybody, and such that its first Betti number is equal n, it's greater than 0. There is a manifold. I called it free abelian couple, maximal free abelian couple, the manifold. So we can take maximal abelian couple. This is in this case that's it's the covering for which the deck transformation is the abelian group, and it's deck transformation from abelian group. It's a maximal abelian group which is possible. Now I take only 3 groups. So in this case, P1 of this covering space. So for any subgroup of P1 of M, to any subgroup there corresponds a covering. So let's take first they take the abelianization from P1, we go to H1 to the first homology group, and then factorize it via torsion to get the n. So take the kernel of the composition of these two homomorphisms and assume that would be P1 of MA fab. So such a covering exists, and Z and epsilon MA fab freely, and also the quotient of the action is just the manifold M. What are the examples? For instance, take the suspensions of toric automorphism. That's 2 simple cases. Assume we take a torus R2 over Z2 and take the matrix toric automorphism, which is given by this nilpotent matrix. So we take multiply a torus T2 by the interval and glue it 2 copies of the boundary by this automorphism. You will get nil manifold on which there is realized this nilpotent Thurston geometry. It's well known from 3-dimensional manifolds, and it's maximal. So first homology group doesn't have torsion. So this is in this case MA fab. It's also maximal abelian cave in it S1 cross R2. So the second Betti number is equal to. Even the previous example, we replace it by this hyperbolic matrix A. We obtain a solved manifold on which the Thurston solvable geometry is realized, and the maximum abelian cave would be T2 times R. So in this case, n equal 1. Interesting also the case that M is a closed oriented surface of genus G. Then again, maximum abelian cave is the Riemann surface of infinite genus, such that Z to G exonates freely and the vector of these Riemann surfaces. In this case, n is equal to G. Now, what is let's consider the action of Z10 on M fab. Let's lambda they would be Zn. This is this lattice, and Z1, Z2, and so Zn be cycles which form a basis in lambda. We take closed one forms which form a basis in the first cohomology group, the rank cohomology group, such that this basis is dual to this cycle. So action of omega g in IZL is delta GL. So they're dual basis in cohomology. Actually, I can write here first cohomology group with coefficients in Z, but because they're realizing these cocycles. The pullbacks of this form onto this cover are the differentials of the functions. We do have some functions here. Has to be not FLHL, sorry, HL, yeah, where P is the covering. So what is generalized FB function? Flaquet block functions. The lambda acts on this covering and take its generators. We take the functions, these functions satisfy this, we can generate in such a form that they are related to this function as follows. AG T, here has to be TL of X equal AGX plus delta GL. So then we X on X by the nth deck transformation, then the value of H is shifted by delta GL. This is actually the same as this duality. It's just, I write this duality. An analog of the function is defined condition that this is the function of this is covering. And it has this form, psi TL x is equal exponent IKL, because here the basis is 1, and psi x. And they have this K1K quasi-moment. They are defined up to 2 PM. So that's if you consider the case when the M is a torus, this is just the straightforward generalization of these block functions for tori. It's a block function. Now we take the block function if and only if it's represented in this form. That's again well-known form. There phi is lambda periodic. In the case of tori, this H1, Hn, it's linear, it's coordinate functions on Rn. Here we take this H. Now we can take the generalized Flaquet block spectrum for this operator. It is the same as before. We take the Laplace-Beltrami operator. Then the proof is basically the same. Then there is an analytic set of this form, such that Q belongs to this analytic set if and only if there exists the generalized Flaquet block function with this quasi-momenta, such that its energy is equal to E. What's the point here? The point here, what we are working on Riemannian manifold. So we have to work with different Sobolev spaces. So all these quantities L2, W212 has to be replaced. We've said that these important properties for which we are seeking, so which are necessary for us to reduce in this problem of the existence of the generalized Flaquet block function to the solvability of such equation, where A is the polynomial pencil of compact operators. That could be done, actually. There is the book by Thierry Aubert, French mathematician, and an analysis, kind of fundamental text about about the nonlinear analysis on Riemannian manifolds, and he introduced all necessary spaces, which we can use for mimicking exactly the same proof, and the proof is basically the same. Important point, this spectral variety is independent of the choice of functions. That's also can be checked by straightforward computations. And that these psi functions, which correspond to different choices of H, they're related by multiplication, by even by the function exponent I f. So there f is a real valued function. So in such a way that even the correlators between these psi functions are preserved. So we just only changing the phases of the eigenfunctions. That's the picture. And the final remark. Let's consider this equation. This we did study. It's rewritten in this form. Clearly. That is the magnetic Laplacian for the magnetic field with this potential. So we take the quasi-momenta k multiplied by omega n. We do have one-dimensional form. Add it here, it's real valued form. If k is real valued, then it's real valued. And we do have this potential of a magnetic field. And we have this magnetic potential. So the problem, so this spectral variety explains if you will get this vector potential of this magnetic field with given k1, kn, then if fix them, then f at e equals 0 only at the points of the discrete spectrum of this operator. The final point that this vector potential d of a equals 0, so it's the potential of the zero magnetic field. So that's complications. That demonstrates some complications in the trying to define the magnetic Laplacian on the manifold with non-trivial first Betti number. So because even the formally quantize the zero magnetic field, we can have some strange spectral varieties that I don't understand yet, because I came back from this remark to definition of this Flaquet block spectrum. So we do have actually the analytic deformation extension of this discrete spectrum of operator, Schrödinger operator, of this form actually. That sounds quite interesting. It's I think it's related to the Aronoff-Bohm effects and so on, but it needs to think more about that. But basically, this reducible equation existence, this exactly this equation. Let I write it. Analog of this equation. Analog of this equation on phi would be just the magnetic Laplacian for trivial magnetic field, zero magnetic field, with a very strange choice of potentials. And such choice exists in the case that the first Betti number is positive. Here I would like to stop and thank you for your attention.
Well, thank you very much for the very interesting talk. Are there any questions? Well, maybe I have a question. If you consider this Schrödinger operator on a simply connected manifold and to try to construct semi-classical asymptotics, how does your construction reflect in the quantization conditions on the corresponding Lagrangian manifolds?
On a simply connected or non-simply connected?
Non-simply connected.
That's I don't know yet. I thought this is very recent consideration. Yes, that's a very interesting question. That's what actually is related to my other interest, to our works with Yuri Kortnikov and so on. That's true. Yes, I didn't look at that. But actually, then semi-classical asymptotic analysis can show that this relation between E and K is non-trivial. It has to be non-trivial. It has to form the K, because when we vary K, F varies. So because it would be, this deformation would be trivial if for all the case only if this entire function depends only on E. And it's just fixed discrete spectrum, and then we're changing quasi-momentum, we'll still get this discrete spectrum. But in this case, in the classical analysis, I think demonstrates that this relation is non-trivial. K1 and Kn, this quasi-momenta are coming to this dispersion relation non-trivial. This, I think, the asymptotic analysis is helpful.
Yeah, probably tonal effects can play a role in this problem. Yes, and tunnelen, I mean, between yeah.
But now I just think that this is funny. So I wanted to get this deformation of the discrete spectrum by these parameters coming from here, from this very strange quantization of the zero magnetic field, and it appears they're giving you some deformation spectrum, which is actually some additional spectral characteristics, and it's exactly the same spectral characteristics as, of course, with these Bloch varieties for the case of Torre.
Okay. Well, okay, thank you. Are there any other questions? Well, this seems not to be the case, so we would like to thank the speaker once more. And we have a break until 10:40.